Now that we've already discussed issues relating to pressure and Archimedes' principle, Pascal's principle, and so forth, we're going to finish up our discussion of fluids with two guiding principles, and these are the continuity equation and Bernoulli's principle, or Bernoulli's equation. Okay, now first things first, this idea of continuity, okay, is very, very important, but the basic idea is, suppose that you have some sort of pipe through which you have some fluid flow, but then the pipe constricts. Okay? And so we're going to call the larger section with cross-sectional area A1, okay, and we'll call the cross-sectional area of the smaller pipe A2, all right? And so the idea is this: suppose the pipe is filled with an incompressible fluid. So again, the whole idea of incompressible fluid means the density doesn't change. Okay? And furthermore, suppose that the fluid is flowing through the pipe such that it's in region A first, so it's flowing through region A, or not region A, but region 1, with velocity 1. And then as the pipe constricts, it then starts to flow with a new velocity, v2. Okay? So the word continuity, right? The word continuity means that things aren't changing. This process is continuous, in other words. Okay? So the entire idea behind the continuity equation is that the flow rate is constant. In other words, if I look at a chunk of mass inside the larger area, okay, this mass has to flow through the pipe in a time interval equivalent to that same mass in the smaller pipe. Okay, so the flow rate is constant. Equal amounts of mass are flowing with equal rates. Okay, and what we can draw from this is that if this is the case, if the flow rate has to be constant, then the velocity in region 2 has to be larger than the velocity in region 1, because A1 is larger than A2. So the only way for the fluid to be able to be pushed at the same rate is to be moving faster through the smaller nozzle. Okay? So what this leads to, this is an inverse proportionality. Okay. Um, so what this means is that V2 over V1 is this ratio must be the same, since these have to be proportional, as A1 to A2. And that directly leads to this proportion, or not the proportion anymore. If I cross multiply, A1 times V1 equals A2 times V2. Okay? So whatever my cross-sectional area in the first part of my pipe is, times its velocity must be equal to the cross-sectional area in the second part of the pipe times the velocity there. Now, in our example, we're going from a large portion of pipe to a smaller portion of pipe, but the reverse is true. If I were going from a smaller portion of pipe to a larger portion of pipe, then whatever the velocity here in this first portion would be, the velocity here would have to be smaller. All right, if A1 was less than A2, right? So this equation is universal for pipes that have fluid completely filled, and they have pressure sources that are pushing the fluid through the pipes. Then this equation has to be true. Okay, so this result is just basically saying this chunk of mass is going to flow through the pipe at some rate, and that same rate will be this chunk of mass if those masses are the same. In one case, you have a larger area, so you have a smaller thickness, whereas here you have a larger thickness because you have a smaller area. Okay, so this total amount of mass is going to move through the pipe with the same rate that this mass will. Right? So that's the idea of continuity, okay? That the flow rate has to be the same. So what does Bernoulli's equation have to say? Okay? So Bernoulli's equation is your conservation of energy. Okay. Now, suppose, okay, we're gonna make this situation a little bit more complicated, but suppose I have a pipe with cross-sectional area A1, and not only does the pipe kind of constrict a little, but the pipe actually changes elevation. Let me draw that so that the areas are a little bit more noticeably different. Okay. So now I have cross-sectional area A2, all right? And by the same token, okay, I have some chunk of mass in this first pipe, well, in the first section of the pipe. And so my chunk of mass might look like this. And it will have delta x1. And up here, it'll be stretched out from the consideration that we just had from the continuity equation. Okay. And by the way, the fluid will all have density rho. Okay. And this piece of mass will have volume element delta V, And this one will also have delta V, but well, let's call this delta V1, this is delta V2. But if mass 1 equals mass 2, we're looking at the same amount of mass, then rho dV1 must, we're using deltas, so let me come back. Rho delta V1 must equal rho delta V2. And since our densities cancel out, we can see that these total volumes have to be the same. Okay? Now, this is going to be flowing with rate V1 in this part of the pipe, and it'll be flowing with rate V2 in this part of the pipe, right? Okay. Now, the force being exerted on this back end of the pipe, or on the fluid rather, okay, F1 is going to equal the pressure in the rear times A1, and F2, the pressure over here is going to be pushing inward this way, and that must be pressure 2 times area 2. Okay? So, also, we have lifted this mass by some height h. Okay? So we've lifted the mass from here up to here. So let me actually draw that just a little bit better. So this height right here is h. Okay? Now, the entire idea behind Bernoulli's equation is doing work calculations. Okay? So the total work done, delta W, is equal to the force of the work done by F1, in other words. So F1 times delta X1, that was the work involved in moving this chunk of mass from here to here, minus the work done by force 2 times delta X2. So the pressure at the front end is trying to push the fluid backward against the pressure from the other end. All right. So your total work done, or the net work, or your change in work, is going to be the difference between these two amounts of work. Right? But if we insert this, these definitions of F1 and F2 into this equation, my net work is going to become P1 times A1 times delta X1 minus P2 A2 delta X2. And if we look at A times delta X, well, that's just delta V. Our cross-sectional area times our displacement so this becomes P1 delta V1 minus P2 delta V2, and then we can factor out our delta V's. Because delta V1 equals delta V2, I can drop the subscripts on my volume elements, and we have P1 minus P2 times delta V. Okay? So this is the work that's done on the fluid. And obviously the work done on the fluid has to be positive because the fluid is moving, right? So this is the work. And by the way, this is work done by non-conservative forces. Okay? So, in other words, the whatever's creating the pressure on this end to push the fluid through the pipe is going to be some external mechanism. It's not going to be a conservative process. Okay, so that's the idea there. But we have three components to our energy. We have work, we have kinetic energy, and we have potential energy. So we've taken care of the work, and now it's time to look at the kinetic energy. So the kinetic energy, or the change in my kinetic energy, and note that the kinetic energy does not necessarily have to stay constant through this process, right? Because even though the rate at which things are moving through is going to be the same, because kinetic energy depends not just on the rate of mass moving, but the rate of the speed squared. So even though the rate at which the mass is moving through, the kinetic energy of that mass does not have to stay constant. Okay? So that's the bottom line. That's the punchline. So delta KE is going to be 1/2 mv1 squared minus 1/2 mv2 squared. Now, these are velocities, not volumes. So I will try to stick with the convention that volumes here are capital V's. Okay. So think of these as capital V's and velocity as lowercase v. All right? Okay. And so, with that, but remember that mass is equal to our density times our delta V. And maybe we'll try to use script V's for velocities. Okay. And so once again, I can factor some things out here, right? So this is 1/2 rho delta V times V1 squared minus V2 squared, right? Whoops. I have my subscripts turned around because change is final minus initial. So these subscripts need to be turned around. But nothing major. Okay. And then finally, okay, we need to look at the change in potential energy. Now, of course, there's no elastic potential energy here. Everything is gravitational. So this is going to be equal to m times g times y. Let's call it h. Let's call this h final, maybe. And let's call this h initial. Okay. So, whoops, went the wrong way. So this is going to be mg h final minus mg h initial, and this is equal to rho times delta v times g times h2 minus rho times delta V times G times H naught. Okay, and so once again, we can factor out rho delta VG, and then we get H2 minus H1. All right, now, so here's the kicker. Remember that the work done by non-conservative forces is equal to the change in total energy. Okay, so the work done by our pressure forces, the whatever's pumping the water through, this pressure 1 minus pressure 2 delta V, is going to be equal to the change in kinetic energy plus the change in the potential energy. So this is going to be 1/2 rho delta V, V2 squared minus V1 squared, plus rho delta V times G H2 minus H1. Okay, so we're getting there, all right? But first thing to notice, my delta V's cancel out. My volumes cancel out everywhere, all right? And the next thing to note, well, so the way we classically write this, all right, is to group our 2's on one side and our 1's on the other side, our subscripts. Okay, so if I pull all of the 1's onto one side, I get P1 plus this 1/2 rho V1 squared plus rho G H1, not P but rho, is equal to, I'm going to move P2 over to this side, and then I'm going to be left with plus 1/2 rho V2 squared plus rho G H2. Okay? So there's a couple of things to observe here. These terms, okay, 1/2 rho V1 squared is kinetic energy per unit volume. Okay? And rho GH is potential energy per unit volume. And pressure is equal to energy per unit volume. And these have to agree, or else our dimensional analysis won't work, right? But remember that force is equal to pressure, pressure is equal to force over area. Right? Pressure is equal to force over area, but work, or force is equal to work times I'm getting all tongue-tied. Work is equal to force times displacement, so force is equal to work per displacement. But work per displacement divided by area is the same thing as work per volume. Okay, so pressure, you can think of pressure as either a force per unit area or as an energy per unit volume. Okay, And that's what this equation is telling you. The energy per unit volume in one side of the pipe has to equal the energy per unit volume in the second part of the pipe. Okay? So this is the basic idea behind Bernoulli's equation, and we generally just shorten this down to say, well, if everywhere in the pipe, if this equation must hold true, then we can generalize that to say that the pressure anywhere in the pipe plus the kinetic energy per unit volume plus the potential energy per unit volume must be a constant. Okay? So now let's come back to that original picture where we had the pipe like this. Let me see if I can draw that a little bit better. Hey, that looks a little bit better. Maybe not a ton, but a little bit. Okay? So area A1 out here, area A2 out here. Okay? Now, there's a very important conclusion to be drawn here. Okay? And that is this. So for the moment, we're going to assume that there's really no change in potential energy. Okay, the central axis of the pipe doesn't change height, so there's no net change in height for any of our mass elements of our water. Okay. In this case, then the equation reads P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. So the delta change in potential energy is equal to 0. So notice, okay, if I combine Bernoulli's equation with the equation of continuity, what this predicts. So, here it is. There's a very common misconception that when you constrict the nozzle of a hose, like with water in it, right, like a garden hose, you're told to go spray the flowers with the water. And so one very common thing you do is you turn on the water and then you stick your finger over part of the hose and the water squirts out at a much higher speed, right? You get a lot more arc on your water. So the common misconception is that by placing your thumb over the nozzle, that you are increasing the pressure because the water seems to be more backed up, and so then that pressure forces the water that can come out at a higher rate. Okay, this is incorrect, and it's a combination of the equation of continuity and the Bernoulli equation that we can see why this is incorrect, but here it is. Okay, so my pressure P1 in this region with velocity 1, when I constrict my pipe, the velocity increases via inversely proportional to the ratio of the areas. So whatever the ratio of A1 to A2 is, that'll be the ratio of V2 to V1. Okay? So if A1 is larger than A2, then V2 is larger than V1. Okay? But what does the continuity, or not the continuity, but Bernoulli's equation say? Okay? So if V2 is higher than V1, then kinetic energy 2 compared to kinetic energy 1, we must have KE2 is greater than kinetic energy 1. So that implies that if K2 is larger, KE2 is larger than KE1, for this equality to hold true, then P1 must be larger than P2. Okay? So the pressure in a larger part of your pipe is going to be larger than the pressure in the smaller part of your pipe. Let me say that again. The pressure in your larger part of your pipe is going to have a larger value than the pressure in the smaller part of your pipe. Now, once again, we're ignoring changes in gravitational potential energy. But when you have a pipe with a central axis that doesn't have a change in H, then this is going to be absolutely true. Okay? So, when you constrict your garden hose, all right, when you stick your thumb over the garden hose, you're not necessarily increasing the pressure, you're decreasing the pressure, but by the continuity equation, that has to increase the velocity, and it's the increased launch velocity of the water out of the garden hose that gives it the extra distance. Okay, so you're not increasing the pressure in your garden hose. Okay, not at all. In fact, you're actually decreasing the pressure. So this is really the punchline, okay, is these two equations working in concert with each other to then be able to analyze what's going on in a pipe, okay? So there you have the continuity equation, and you have Bernoulli's equation, and these are really, as far as actual fluid flow go, these are two of the most important equations out there, okay, with fluids. These are your starting points for a number of higher order and more complicated situations, okay? So Bernoulli's principle even gives you the starting point for why airplane wings work, right? So, for example, airplane wings are designed such that if the plane is flying this way, then that means the air is kind of moving over the wing like this, right? Well, okay, so you have your air that the wing is flying into, and some of that air gets cut over the wing, and then some of the air, rest of the air goes underneath the wing. So your wing is designed such that the speed of the air that goes over the wing, let's call this V1, and the speed of the air that goes under the wing, it's designed such that V1 is larger than V2. Okay? But if V1 is larger than V2, then that means that pressure 2, the pressure in region 2, has to be larger than the pressure in region 1, above the wing. And that means the force on the bottom of the wing is larger than the force pushing down on the top of the wing. And so it's this force differential. Once again, you have the force from the pressure and area of the wing above. But if P2 is larger than P1, then you will have a larger upward force. And so your lift, what we call the lifting force, and so now, as long as F lift is greater than the mass of the plane times gravity, you can fly. Okay. Now, wings are much more complicated than this. Okay. This is not the end of the story with wings by any stretch of the imagination. But this is the starting point for why to think about how wings work. Okay. Why you're able to generate simple lift in the first place. Okay. But maneuvering and getting the wing to adjust to ever so slight turbulences and all of those kinds of things is far beyond our discussions here. But this is the basic idea. Okay. So that is the continuity equation with Bernoulli's principle. And up next is oscillations.